record this session on this computer, and then I'll share it with you. And let me share my screen to get it go. Okay, so scores on your quiz 1, you will receive maybe today or tomorrow. We don't actually concern more about the scores because all of you would get better scores. That's not a problem. The process of, I mean, why we have all these quizzes and evaluation is just to evaluate yourself, how much you've learned from the lecture session. So it's your own evaluation. You're evaluating for yourself, and you have a professor here who is helping with this evaluation process. So try to make best use of it and try to improve further with the comments that you will receive from me. Okay.
Sorry, may I
Yes.
mention something? I think the deadline on the Moodle was wrong. It was something like 10 a.m. or 11 a.m. So if you mean that some students were late, we got this notification that we are submitting late, but it was wrong. It was not midnight of Wednesday.
Oh, so it was, I think instead of 23:59, I might have chosen 11:59. And that might have created a problem.
Maybe AM you chose instead of PM, something.
Yes, yes. Now, thanks for this clarification, Majid. I really
No
appreciate
worries.
it. Definitely, it might have been the problem that, because you know, there on Moodle, the timing is in terms of hours and not AM or PM. So I might have selected 11:59, whereas I should have selected 23:59. That makes it midnight. Okay.
That's right. I didn't mention it because I knew you know yourself. It's
I
midnight.
understand.
Wednesday.
Yes, that's true. That's true. So no one is late. No one is late.
I don't think anyone is late.
Good. Thanks for telling me this. And yeah, I'll take you next time as well. So, for today's session, I've selected this topic where we'll discuss biomechanics of upper limb and related injuries. And we'll also try to go through various commercial devices that are available for such kind of upper limb related injuries and disabilities. So, before going into the biomechanics of upper limb, I would also take some time to explain you how do we capture data, how do we take measurements, and so on that part, I'll talk about little about the three-dimensional kinematics, three-dimensional space, and how do we make the measurements. So this is, as you can see in the picture, there's a few markers on the lower limb. These are spatial markers which would reflect light and give us indication on the camera or on the frame that we record. And then we can put all these frame together, and then when you move it, kind of a movie. So each marker would give you a trace. Okay. And so with those traces, we can figure out what is the trajectory of a certain body part, or trajectory of the marker point, and then put together a few marker points, can find out the trajectory of the body part, that limb that we are interested in. And then on the time scale, if you look at it, I'm able to find out what is the velocity, acceleration, and so on and so forth. But the problem is that the markers, they are put on the leg, let's say, okay? And my camera is sitting on the lab floor. And so I should know what is the position of this marker with respect to the ground, isn't it? So for instance, if there's something, if I want to find out, let's say this is your coordinate system, okay? Let's say this is your X, Z, and Y, okay? This is normal convention that we take. And if we have a point which is like 2, 3, 4, okay? What does it mean is that it has 2 unit of distance along X, 3 unit of distance along Y, and then 4 unit of distance along Z, isn't it? So you know this point where it is, right, in this space. And in the next instant, let's say the point has shifted from this place to this place. Okay, so that's a new location. For this, again, I would find out the coordinates. Let's say now the coordinates are 1, 2, and let's say 6. Okay, sorry, yeah, 1 to 6. You know what is it? Okay, so 1 to 6 would mean that 1, 2, and then 6, right? Now we know that it has moved from 2, 3, 4 to 1, 3, 6, or 1 to 6. Now, unless I have this origin and this reference frame of XYZ, I'm not able to find the coordinates. I can only see something is moving, but I cannot find out what's the distance between the 2 points. To find the distance between the 2 points, I need to know the coordinates. To know the coordinates, I need to have this XYZ somewhere. To have XYZ somewhere, it's called a coordinate system or a referencing system. Okay. Now, the referencing system that I'm talking about stays on the ground, on the lab floor where I'm standing, in the lab. And we term it as GRS, which is Global Reference System. So any coordinate system, is denoted by a reference system. When you say a reference system, we actually talking about a coordinate system of these 3 axes X, Y, and Z. So we need to have this X, Y, Z, and then we can find out the coordinates of marker with respect to the system. And then I'm able to do all my calculations and analyze these markers movement with the limb movements. Okay. Now, the problem is that when you look at the human musculoskeletal system, every limb would have its own coordinate system. Can you see this? Right. So what I'm saying is there'll be a coordinate system for the foot, for the leg, thigh section, wrist, forearm, and then you have coordinate system for all these body sections, right? And then you have a coordinate system of the leg. Okay. And so we need to, as I said, finding a coordinate. For instance, if I'm interested in finding this coordinate about this axis, I can figure out maybe this is 2, 5, and 3, whatever, right? Whatever. It's just a random number with respect to this, right? Now, how do I find this? It's very difficult because I need to actually measure where the person's standing. You know my problem? I need to find out where the person is standing and then take all these measurements. Finding these coordinates are very difficult. So what we do is, we don't find the coordinates with respect to the ground system, okay? We find the coordinates. For instance, if I'm interested in this coordinate and this coordinate, I can use a small little coordinate system which is placed on that limb itself and figure out what are the coordinates, okay? And later what I'll do is, I'll try to find a mapping between my global reference system, okay, and this local reference system. Okay. So in a layman's language, what happens is this GRS, okay, is somehow related to LRS, local referencing system. And how is that related? It's quite simple. That there's some kind of a matrix. There's some kind of a matrix, which if I multiply with the local reference system coordinate, it will give me a GRS. So if I'm interested to find GRS for, let's say this coordinate is 2, 3, 5, okay. Oops. So all I need to do is take that matrix and multiply with this 2, 3, 5, and then I get GRS. I get coordinates of this point with respect to the global reference system. It's pretty simple, isn't it? What is not simple, I mean, this seems to be quite simple, but what is not simple is finding this M, this mapping between GRS and this marker reference system or the local reference systems. I need to find a kind of mapping between the two systems. Once I find this M, then it becomes quite easy for me to convert all these coordinates that is being measured in local reference system, and then I can find what they mean with respect to the ground, and then I have all the measurements and I'm fine. The only thing is I need to find this M, and that's a problem. Now, what is this LRS and how do we place it? Okay, so normally the principal axis of each segment is the axis system of this. So if I'm placing a, let's say I'm talking about this particular section of human limb, and so what I'll do is I'll find out the center of mass, and that I'll take as an origin. You know how in all these coordinate systems there's an origin and then you have X, Y, and Z. Okay, so I'll place my origin of the local reference system at the center of mass of the limb, as you can see here, right? And then according to the principal axis of segment, okay, I'll align my X to this, and other axis will be known to me. As you can see, you know, the main the principal axis of the segment, okay, that is taken as the main axis of the local reference system. So you can also call it, as it says, as an anatomical axis system, because it perfectly aligns with the anatomical system and the anatomy of the limbs. So I hope you understand this local reference system, and now I can talk about the global reference system. So if you have any question, you can ask me anytime, okay? You can stop me and you can ask questions. Now for the global reference system, as you can see, we have already defined this previously also, and once again we'll do it. So this X is basically X-axis, direction of the X-axis in the global reference system is basically the forward or the backward direction, okay? Y being the vertical axis opposed to the gravity, okay? This is gravity and it's opposed to y-axis. So this is positive direction. This is positive direction, and this will be the negative direction, okay? Whereas this Z, of course, Z-axis or Z-axis will be left and right, or you can also call it medial or lateral axis directions. So this side is going to be positive, and here will be negative. This is the normal convention that we've discussed before also, and with this system, it becomes clear that the XZ plane is this horizontal plane, okay, right? And so the XY plane would be the sagittal plane, and similarly this YZ plane would be the frontal plane, okay? So that's kind of convention that we normally use. And then how do we place the markers? That's again very interesting. So we have this global reference frame, right? And for the local reference systems, we need markers, we need sensors, there are force plates. Apart from this, there is one more thing that we have. We normally have a rigid bar that is placed onto the sensor. So there's a sensor here, as you can see. And on top of the sensor, there's a plate, and the plate has two markers. Okay. Now, the plate we put there is to check on the inclination angles. Okay. So when there's an inclination, this marker and this marker will give you certain inclination, and the same inclination is given by the sensor also, and then we can validate. So what's happening is you've got a sensor here, okay, and then attached to the sensor is a plate, and you've got a marker 1 here and marker 2 here. So if there's some kind of rotation, okay, so the sensor gives you certain reading. Let's say it gives you some reading θ1, and you can also measure the inclination with the coordinates of M1 and M2. So when the M1 and M2 are like this, okay, and you know their coordinates x, y, z of these two, we are able to determine how much is the angle. And so we will cross tally with this, and we would validate this inclination. So yeah, a spatial calibration system, and then there's a calibration system as well. I haven't talked about it. While we use the markers, we also use, okay, these markers are again two kinds of. One are the measuring markers, the other one is called calibration markers. So what we have is, for instance, if I'm talking about, let's say the trunk section, okay, so I'll put a calibration marker on both sides, and then other markers would be calibrated. So it just to make sure that the measuring markers with respect to the ground, they are at their right positions. You know what is calibration? Calibration is an activity by which we try to standardize the position of these markers. So these calibration markers are especially important when we deal with the patients who cannot stand straight, right? And so if someone cannot stand straight, how do we know that this particular marker belongs to a particular position where it should be? And so for that, we use these calibration markers, their placement, and then, so, well, you don't have to go into this detail of things, but yeah, you can see how this is analogously shown in here as well. So maybe you cannot see those bars and the markers here, but yeah. So these are the markers, and this is that bar, rigid bar where the markers are mounted on. And under this interface, you have the sensors. We'll talk about sensors also sometimes when you get time, but for now, I was talking about this anatomical axis or the local reference system, right? Now, the local reference system or the anatomical axis system, it has to have its origin and also principal axis. So as I was telling you, the origin of local reference system or the anatomical axis system is placed at the center of mass of the segment. Okay. Maybe I can just go back again and show you what I'm saying. Can you see this? So that's the origin of local reference system, which is placed at the center of mass. So if I'm talking about, let's say, this segment, the center of mass would be here. I'm talking about this segment, okay? And its center of mass would be exactly at the center. And this is what I'm trying to say here, that the origin is kept at the center of the segment point. Now, if you talk about the principal axis, okay? Let's say we're talking about the y-axis being the principal axis. And so this y-axis is usually along the long axis of the segment. Okay, so all those blue arrows in the previous slide, they all denote to the y-axis of local reference system. The principal y-axis is, okay, sometimes it is difficult to, figure out, for instance, if you talk about the pelvis joint, pelvis bone, or the hip bone, okay, for the hip bone, how would you determine the long axis, for instance? Okay, so there what we do is we try to join the PSIS and ASIS, the posterior and anterior spine points, okay, extremes. We take these extremes from the pelvis, we connect them, and that becomes our principal axis. Yeah. And then, so once we have those local systems, local reference systems, and we also have a global reference system, now we need to, as I was telling you, we need to find a kind of mapping between global and the local, global and the local. So this matrix is supposed to be giving us back and forth. So if you know the local reference system, local coordinates, you can figure out what are the global coordinates. Or if you know the global coordinates, you can also figure out what are the local coordinates. But in the process, you need two transformations. Okay. Now these two transformations are, first you need to transform from global reference system to the marker axis system. Okay. Now the marker reference system may not be always the anatomical reference system. They might be different. Okay. Because placing markers is again is a very skilled work. You need to identify where your markers can be placed. So there might be differences between the marker reference system and the anatomical reference system. And so from GRS to marker reference system, and then from marker reference system to the anatomical axis. Okay. So what I'm trying to say here is that there's a mapping between G to the anatomical reference system. But before that, we have to find two matrices now, M1 and M2. This M1 would be a matrix that would transform from global to marker reference system. And then this matrix would transform values from marker reference system to anatomical reference system. And put together, this becomes one matrix, which determines this exchange, this conversion between global and the anatomical coordinates. It is shown with some diagram here. For instance, let's say this is your marker reference system, and this is your global reference system. Okay, so we try to find out some sort of a matrix. Those who do not understand matrix, I would suggest please go through, that one PPT file that I shared yesterday on vectors. That probably has information on the matrix. What else? How else I can explain X, Y, Z? So a matrix, you know, for instance, okay, let me try. If there's a direction here, and this direction has been changed to this direction now, okay? So if I'm trying to find the relation between these two, okay, I need to figure out how much x, y, and z values have been changed, okay? So x, y, and z values changed would mean that there's a these are the values for x, y, and z that has changed, and that makes a matrix. And even still, if you do not know, if you don't understand, you don't have to understand. Just remember that there's something of this sort that has to be multiplied with the coordinates, okay? And it'll give you the transition. Well, if time permits, maybe today I'll talk a little about the robotics, and that will give you further idea of what I'm talking about. Now, there's very small small information regarding the vector multiplication that I need to talk about here. So I'll take 1 or 2 slides on that, and then we'll move on. Okay. So when you have 2 vectors, let's saying 1, and let's say this is 2 vectors, we can actually multiply the 2 vectors. Okay. And 2 vectors can be multiplied in 2 ways. One is called the dot multiplication, the other one is called the cross multiplication. Okay. Now, for instance, let's say you have one vector like this, okay? And how do we define vectors is, for instance, let's talk only about 2 axes, like x and y. Okay. And let's say that the coordinates are 2 and 5. So this is 2 and this is 5, right? You understand this. So I can define this vector, whatever name is, I can define this p vector as 2 in x direction plus 5 in y direction. We can denote them by ijk or xy. I can also write it as like 2x plus 5 in y direction. This is how I would denote a vector, okay? Now, so as I said, it could be x, y, and z, or it could be I, j, and k, right? Now, for instance, you have a vector which is, as I mentioned, 2i plus 5j, okay? And let's say there's another vector which is 5i and 2j, okay? So how this vector would look like? It'll be 5 here and 2 here. So it'll be something like this, okay? This is the vector p2. Now, if I want to multiply these 2 vectors, I can do a dot product, or I can do a cross product. So when I do a dot product, it gives me a number. Whereas if I do a cross product, it gives me another vector. Okay. Now let's find out what is a dot product first. For the dot product, it's pretty simple. All you need to do is multiply 2 and 5, and then add multiplication of 5 and 2. And so this is 20. Pretty simple, isn't it? But if you're doing a cross product, it's not that simple. For the cross product, let's move on to the next page. Yeah. So for a cross product, I have to do something kind of this. So once again, let's say we have those similar values where we had only I and j, 2 and 5, 5 and 2, okay? Or let's say this time we got one more, k also there, okay? And let's say it is 1, 1. So when there's a matrix, we use this kind of a bracket, but the value of matrix, how the magnitude or the value of the matrix, if you need to find out, you only draw two vertical lines, and it's called determinant, okay, because we are trying to determine the value of the matrix. And so this kind of expression is called determinant A. Okay, determinant. Okay, I hope you understand this determinant. So this is a determinant, and then finding values, the answers would be, as I said, it'll be again a vector. If you multiply two vectors in a cross product fashion, you give another vector. You get another vector, and this time it'll be for I, you need to hide these two, and then multiply 5 with 1, and then subtract 2 times 1. Okay. Similarly for, okay, one second. Now for J, yeah, for J, you need to cancel these two and then multiply. Okay, minus. We use plus, minus, and then plus signs here. So this will be minus here, J times. So crossing these two, you need to multiply 2 times 1 and then subtract 5 times 1. And for K, it's positive again. And for K, we would cross out these rows and columns. And we'll multiply 2 times 2, which is 4, and subtract 5 times 5, which is 25. So what you get here? You get 5 minus 2 is 3i, and 2 minus 5 is minus 3, and minus here, so minus and minus becomes positive. So it'll be plus 3j, and then you got 4 minus 25, which is minus 25. So you get negative 21k. Okay. So eventually what you get is a vector which can be defined as 3x plus 3j minus 21z. Okay. Yeah. Simple, isn't it? Oh, I've got some examples here. Good. So when you have, let's say, force and velocity defined as this, like 2x plus 4j, velocity defined as x plus 5y, and so the dot product would be multiplication of 2 and 1 and 4 and 5, and then added together, so it'll be 22 clearly. Okay, but if you're trying to find a cross product, so in that case, let's say this is 2 1 minus 1, so 2x plus y minus 3z and this is 4x plus 5. So you can write ijk xyz, right? Two coefficients, 2 1 and minus 3, and then 0 for I, okay, and 4 for y, and 5 for z here. And then you do the same thing for when you're considering I. You cross out the rows and columns where you have I, so it'll be 5 times 1 and 4 times minus 3, and then similarly, okay, and you get another vector. Now with this discussion, you have become an expert in vectors. If someone asks you, how do you know vectors or not, you can easily say that yes, we know the vectors, and we can also multiply the vectors. Okay. So why we need dot products and cross products is because when we find this matrix and when we are multiplying this matrix with the local reference system to get the global reference system, we at times have to do multiplication between the vectors, and that's why I've discussed that here. Back to our discussion of those markers and anatomical axis, right? So this again, for instance, could be thigh section or whatever. Something that I had missed before, that we use marker systems, but with the markers, I was telling, there are two kinds of markers. One is the measurement markers, and the other one are used for the calibration. So as you can see here, this anatomical segment, it shows global reference system, right? And it also has marker axis and anatomical axis. So this is the anatomical axis, which is always situated at the center of mass of the limb. Okay, that's the anatomical axis. And then you have measuring or the tracking markers. And then you have calibration markers. So for instance, these are two calibration markers, 1 and 2. They would tell me the location of this limb, okay? And then I can figure out what is the location of the center of mass. The other markers, they are situated here, 1, 2, 3. These 3 tracking markers would give me the trace and their coordinates I can find out. So I need to find out conversion from marker axis to the anatomical axis. That's one thing. And then I can figure out what is the conversion from global system to the marker system. Okay. And then if I want to find from global to anatomical, it's going to be product of G to M and M to A. And this is how you can find what is G to A. It's the same story here, shown with this illustration, and it helps you understanding that you have a global system and the marker system and the marker axis. Okay. And with this, you get G to M matrix, that's M1, let's say. And then from marker to calibration to the anatomical, you get M2A matrix, let's say this is M2. And multiplying these two together, you get G, another M. So you can write G is M times A, where M is what? It's a multiplication of M1 and M2. Okay. So we do need these markers and marker system and the anatomical axis system information so that we're able to, make, whatever measures that we've taken, we can put all these measures in one reference frame and then we can compare them along. So for instance, if you have a patient coming to you and then you would like to, the patient cannot stand straight or whatever, but with this information, I can figure out with the markers position, I can figure out where it relates to and where it should be, and then I can offset any displacement that exists with the disabled person. Well, we were supposed to talk about the biomechanics. So this is all about the measuring. Let's talk about biomechanics that we wanted to read, study at first. So there we actually try to find a relation, the interrelation that exists between the skeletal system, muscles, joints. Okay. So essentially, we're talking about the upper limb. Okay. So we may be interested in the shoulder joint where we try to understand clavicle, scapula, girdle, all that. Then it comes down to the humerus bone. Then we have elbow joint. And then we have radius and ulna bones, and then the wrist joint and other bones. So biomechanics, when you call it biomechanics, it has a word of mechanics there. Okay. Do you remember the mechanics that we were talking about? So for instance, if you have a limb of mass M and it's pivoted here, and so when you apply a force here, this end would go up. If I apply a force downward here, because it is hinged here, this end of the mass will tend to move upward because there's an this force is this is the force and this is distance r. Okay, so because of by virtue of this force, there'll be a torque acting at the hinge, and that torque or the moment we define as r times F, right? So this mechanics goes on, but we need to identify what are these segments. What is this M? What is this hinge? And what is this force? Isn't it? So the force always comes from the muscles. M definitely is going to be the bone, and where it is hinged is the question. It could be ligaments or it could be other soft tissues. So the bones, they form the liver. This is the liver. Okay. The ligaments, they form the hinges, and the muscles that they act to apply the forces to move the livers about the joints. Okay. So for instance, here we did this in walking. You know, if you remember this. So the force acted upon by the muscle. Okay. And this acts as a hinge, and this is the segment. Okay. And so with this force applied by the muscle, there'll be force on the ground, isn't it? See, if I apply force downward, there's a force upward here. So if I apply force upward, there'll be a force downward. Okay, so you tend to push the earth, and because you're pushing the earth, there'll be a reaction force. If there's no reaction force, you cannot walk. You know that? If you try to walk on, let's say, ice, snow, ice. If you want to walk on ice, it's hard to walk because there's no friction, and because there's no friction, there's no reaction. This reaction basically is multiplication of friction times the weight. So when there's no friction, there's no reaction force, and you cannot walk. So you understand how there's a hinge, there's a force, and there's a reaction force. Okay. Moving further on. Yeah. These anatomical joints that I'm talking about, they are normally described in terms of degrees of freedom. Okay. For instance, if I talk about my elbow joint, I would say that because I can only rotate it, and that too in one plane, it has 1 degree of freedom. Of course, there's some abduction adduction as well, very small amount of it, but we can't probably neglect that. And I'll talk about this, how much and why and how much we can neglect. Now, for example, take your hand and grip. So these interphalangeal joints, okay, how many? They're again uniaxial, and so because they can only move in one plane and one direction, they are again called 1 degree of freedom joints. Okay. And so why we have this degrees of freedom, and why? So if I place something in space, okay, it is said to be having 6 degrees of freedom, because something put in space can travel along x, y, and z directions, and it can also rotate about these axes. So it is said to be having right. Sorry.
Is the thumb also 1 degree of freedom? Because it goes a bit on the other side, no, up.
Yeah. So you could call that, but when you talk about the phalanges, it'll make difference. Okay. But if you talk about the thumb joint, right, it can actually have more than one. Right? Can you see this?
Yeah.
I can move it like this, and I can also move it like this.
That's right.
Do you know how many? So the total number of degrees of freedom for the entire hand is close to 40.
Wow.
But yeah, so why we I was talking about a point in free space would have 6 degrees of freedom, and why we have restricted motion, like reduced degrees of freedom, is because they are constrained by these soft elements and soft tissues, as
Yeah.
well as the cognition. Yeah. Okay. Now, so the description of motion becomes detailed when we talk about the multi-axial joints. For instance, if you talk about the glenohumeral joint, it's not easy. It's quite typical complex. For instance, let's see here. This is your shoulder complex, which has both the shoulder joint and the girdle. So the entire shoulder movement, it is a result of the shoulder joint and the shoulder girdle. Now, if you're talking about the girdle, shoulder girdle, it has clavicle, scapula. Now, so the shoulder girdle, it comprises of this clavicle joint, and also so the clavicle joint, there are 2 here, right? And it also has an ST joint, which is this is very difficult to actually explain. So how your scapula glides on the thorax, when you move like this, so the scapula, it moves on the thorax, and so this scapulo-thoracic joint, this alone, this joint has I think 5 together with everything. It makes 5, I think. Let's see. So the SC and AC joints, they have 3 degrees of freedom for each. So 3 degrees of freedom here, and 3 degrees of freedom here again. Now ST joint, as I was saying, it has 5 degrees of freedom. And it's very difficult to kind of quantify. And so what happens is, together with these 3 joints, SC, AC, and the ST joint, they contribute to this glenohumeral joint finally. I mean, the movement of this center of the glenohumeral joint. Now I cannot actually, I mean, well, we were trying to do this. One of my PhD student, what he's trying to do is, because it's so complex, we try to model scapular motion over the girdle as an ellipsoid, and we did come up with some sort of an algorithm that can predict its motion, but that wasn't very accurate. So finally, one of my students, what he's doing is, he's taking the entire shoulder and he's trying to create a robotic model of it. So a model means it's something that you cannot understand, but you know the output motion, like from the glenohumeral joint. I know what are the output motion if my input muscles are acting in a certain way. So he's trying to create a robotic model that he'll input the muscle forces in, and the result would be the motion of the humerus. And so he's trying to map these 2, and inside them he'll create a robot that will act as a shoulder joint. But that's a different story. We do have such software models available that can provide you that can model the entire shoulder joint. But to make it more simple, what we do is when we have these robots that we use for rehabilitation, they would only consider this. They would not go what's going inside. And so if I simply consider these 3 degrees of freedom at the shoulder joint, superficially, so that actually does my job pretty nicely. And so as you can see here, I would only consider the shoulder joint to be kind of a ball and socket, the glenohumeral joint. And so if it is a ball and socket, kind of this, ball and socket means there's a socket and there's a ball here, okay? And this can move in 3 rotational degrees of freedom. So it has 3 rotational degrees of freedom, as you can see. Yeah. But then if you talk about the girdle, definitely it has 4 movements, okay? What we are interested is the elevation and the depression. And then we are also interested in protraction and the retraction, which is here. So you can have flexion, extension, abduction, adduction, as you can see. You can also rotate internally, externally, and you can have both elevation and depression with it from the girdle, coming from the girdle. So from the girdle, you get elevation and depression, and also protraction and retraction, and they range of motion. Okay. So for instance, if I'm trying to use a robot for the entire upper limb, so I need to look at the biomechanics. So here I've got 3 rotational degrees of freedom. I can only consider flexion extension here. And for this pronation supination, I can, together with this, I can also consider some abduction adduction. And that should be fine. So we try to create such kind of equivalence with the exoskeleton things. And so an exoskeleton creator should be something like this. I mean, robots for the upper limb rehabilitation would be 2 kinds of. One is called an effector type of robot. The other one is called exoskeleton. So I'll have to explain you later what are an effector robots, but you know what are the exoskeletons. So exoskeletons are the robots that are attached to the human limb and they have similar anatomy. And so we'll, towards the end of this lecture, we'll see some of the devices that are being used for upper limb rehabilitation. You would see what is the difference between the exoskeleton and the an effector type of robots. But essentially, any kind of robot that you're using for rehabilitation, it should be able to provide you the required motions of the upper limb, including the shoulder, elbow, wrist. For instance, the wrist motions can be both flexion and extension, and can also be radial and ulnar deviations. And you're able to move your wrist with pronation and supination with the help of elbow joint. When you talk about your fingers, they also give some degrees of freedom. And as you can see, this distal, interphalangeal, and proximal ones. So you get 1 degree of freedom at each of these. And yeah, so I mean, that's how total number of degrees of freedom for the wrist, it becomes so large. All right. So when we're studying the biomechanics of the upper limb motion, okay? So we need to understand the difference between the normal arc of movement and also the functional arc of movement. For instance, let's take an example of the elbow joint, which has a normal arc of flexion extension from 0 to 150 degrees. 0 to 150 degrees, okay? And then it can also give me pronation and supination of 75 to 85 degrees. Okay. Now, creating such kind of a robot is a nuisance. It's pretty difficult. We cannot create a robot that can give you such kind of flexibility. It's very difficult. And so, with the studies, people have come down to a conclusion that you don't need all this. You don't need the normal arc, whereas you only need a functional arc. Okay. And what does a functional arc mean? The functional arc is the one which should be able to provide you movements that are required for everyday life activities. Okay. So, for instance, instead of 0 to 150 degrees, you can only do with 30 to 130 degrees. So all you need is not 150 degrees of deflection, but you need 100 degrees of displacement from the robot. So if you disagree with me at any point of time or have any question, you can always stop me. So they've figured out some studies have been conducted. You can read this paper if you're interested. So they, with various kinds of activities, they have measured what are the elbow flexion required. For instance, the maximum elbow flexion you would need is picking up the phone. That was the earlier case, but still you need to take your phone out from your pocket and then use it. So that's the maximum one. And then opening a door, putting a chair, reading a newspaper, using knife, fork, glass, all these would have different. So eventually it turns out that out of 150 from 0, the functional arc would be this one, which is close to 100 degrees of displacement. And if you talk about the pronation and supination, again, almost equal amount of pronation and supination, like 50 degrees on both sides should be fine. Instead of 75 on one side and 85 on the other side, that makes 160 degrees. So you could do with 100 instead of 160 degrees. Okay. And again, yeah. So it's the same thing with the forearm supination, pronation as well. Because that's what we normally use this pronation, supination is for feeding or dressing tasks like tying a knot or whatever. This is for the supination and pronation. You can check and understand how, for different kinds of these tasks, the functional range is narrower than the normal range. Moving further, the wrist. If you talk about the wrist joint, it has a normal arc of, for instance, flexion of 80 to 85 degrees, and then extension of 70 degrees, a radial deviation of a deviation in the radial direction close to 20 degrees, and the ulnar direction is close to 30 degrees again, 20 to 30 degrees. But then you would need after examining so many people, person with this research paper that I'm quoting here, person has figured out that the entirety of these tasks could be accomplished with 60 degrees of extension instead of 80 to 85 degrees. I mean, 70 degrees of, so 70 degrees of extension is not required, whereas you need only 60 degrees of extension. 54 degrees of flexion instead of 80 to 85. 30 degrees of ulnar and 70 degrees of radial deviations. Well, there isn't much difference, but yeah, there's a lot of difference between the extension and the flexion values. So eventually they say that it comes out to 70% functional range of motion comes out to close to 70% of the normal range of motion normal range of motions or the maximum range of wrist motions. So, which means that 40 degrees of flexion and extension, okay, and put together radial and ulnar, you can need 40 degrees. And it's been shown here for the shoulder again. You can see how the functional space is less than the normal arc. For various tasks that you need to carry out, again, the shaded area shows that you need restricted movement and you don't actually use the full range of motion. So during rehabilitation robots, you can consider this, and that helps in easy design and comfortable use of these rehabilitation robots. Otherwise, sometimes, if the range of motion is too large, and if you make an exoskeleton that goes far away, sometimes it's not possible to bring it back. And so if it's not possible to bring it back, it's of no use. We call it singularity postures. So there are certain singular postures or singular positions in the entirety of the workspace that we move our limbs around. We try to avoid those singular positions and singular points in the space, because if you take robot to those positions, you cannot come back. This is also defined with the term called dexterity. So I hope you know these terms. Yeah, not all of you would know, of course, but yeah. So those who have difficulty in understanding some of the terminologies that we use here, they can try to read more about these definitions and try to understand. So what happens once you have some sort of an injury? So the injuries can restrict your motions, and so for instance, a lesson on to the upper motor neuron and then peripheral nerves, it may result in loss of volition control, motor control, and sensation and the proprioception sometimes, the ability to balance yourself. So once we understand the normal mechanics, okay, and the functional essential components of the hand functions, for instance, there's something more that talks about special activity that needs to be carried out, for instance, writing or sewing, or that also need to be understood, because we need to interact with the patient and understand what exactly kind of work the person has been doing, and so what are the functional hand essential for this person. Okay. In general, if we talk about these functional hand essentials, there are 7 basic movements or maneuvers that we know, and these include. I would just read out these functional hand essentials, and the details you can read yourself. So, a precision tip pinch would be to if you were to lift a pin, let's say, from the table, on top of the table, So this is the precision tip pinch, and a positional pinch would be something like this, when you're holding something. Okay, if you read through, it would further explain like what happens in the thumb position is that the first dorsal interosseous contraction, and then together with this index profundus flexion. So you can also measure how much is the force applied here if you're holding a dynamometer here, which comes in the form of a strap. And this is a lateral pinch, as you can see. You can pinch yourself sometimes to keep yourself awake. And then you have directional grip like this, a hook grip, then a power grasp, and also you can have a span or cylindrical grasp where the dip and the proximal interphalangeal joint, they flex to approximately 30 degrees, and the thumb is embedded. So these are those 7 functional hand essentials. But then with the injuries, some of these would get compromised, and so even if you could work with just thumb and finger pinch and this palmar grip, you should be fine. Yeah. So it says upper limb stroke patients are normally miserable. They become disabled because of hemiplegia on either one side or both, and that results into weakening of arm, and they cannot pick up or reach out or hold something. And so the important goal for the person would be to improve the arm movement and promote the recovery of lost functions. So basically, now what I'm talking about here is like what happens with when the person has a stroke or something. So it eventually impacts the motor control. Okay, and rest you can do yourself. Yeah, there's nothing important here. I can just skip. So few slides I'll be skipping quickly because it's for your information sake, and you can read and understand. So with the poor motor functions, what else? It may also reduce the sensory process. Okay, and so it makes it difficult to carry out all the everyday life activities. Um, Now the central nervous system is affected, and so the entire thing gets disrupted. It restricts. I mean, the disruption would be in the form of restricted range of motion, loss of sensory functions, shoulder pain sometimes, and increased muscle tone. Okay, so muscles become very stiff and cannot move and results into pain. Also, this is in terms of movements, and then in terms of talk, again, it is compromised. Okay, and with the talk, with the force applying capabilities compromised, person cannot hold on something, and so yeah, these are the basic motor function that becomes compromised after a stroke. Talking about the shoulder joint again, you have similar abnormalities that you come across, and so the major goal of rehabilitation would be the functional restoration of the person back to the reinstating the previous the functions and strengths that the person had. But I'm feeling like, okay, it's 11:25, which means we have done like close to 1 hour. Okay, let me come to a point where I can stop. Yeah, for the elbow again, they have difficulty to move their arm normally because of this contracture of the elbow joint. I understand this. And so for instance, when you extend your arm, okay, the bicep muscles are activated, okay, and they generate the flexion torque via the stretch reflex. That's true. And on the other side, when you extend, it is done when you flex it. When you flex it, of course, the triceps would work, okay, and they create the extension torque in the joint, okay. Yeah. And similarly, there would be effect on the wrist and the fingers, and various things mentioned such as muscle atrophy, contractures. So you can just read around those who do not understand these words, and it's very interesting to learn about post-stroke patients and these dysfunctions. Yeah. And then of course the bones would be affected as well. I mean, bones are not affected by the stroke as such, but they're more affected due to muscle stiffness, and now you're not able to use the bones, right? So when you're not moving your limbs at all, right? So what happens is this decreased use of your limbs, it results into osteoporosis, or sometimes it also results into bone resorption. So while the bone was supposed to be absorbing calcium, it starts resorption, and it goes into the blood eventually. The calcium, instead of going towards the bones, it goes out of the bones to the blood. So it does have an effect on the bones in some manner. So compared with the healthy person, a stroke patient would have significant bone density, reduced bone density. Okay, it is found that 8% reduction in the bone density, and was found in one particular case, says female stroke patients have 8% lower bone density. There's another report that has mentioned that in hemiplegic hens, the bone density reduction was found to be 2.8% along 1% related to the contralateral side of post-stroke interval. So in just 4 weeks of time, as you can see, the bone density can go down to like 10 to 11%. So the first thing that's why the first thing is to rehabilitate the range of motions, and after this treatment that is called RICE, R-I-C-E, we try to come back to the range of motion exercise as quickly as soon as possible, starting from the wrist joint, and then so that the bone degradation can be stopped. And but apart from the bones, even the muscles, they have effect in terms of, I was talking about the bone muscle atrophy, and so the issue of bone resorption, it's again because of this muscle atrophy. So stiffness in the muscles was significantly higher than the normal humans. Obviously, it would be because there's neuroplasticity. It has been broken, and then the muscles are not getting any signal, and they become stiff over the time. So we also need to sometimes quantify how much are the muscles affected, and how much the cartilage is affected. The cartilages again have, for instance, thickness will be decreased, for instance, and the only region is this immobilization of the joint after the stroke. Okay. So let's quickly conclude it. So, though we do not have a universal evaluation criteria, but we understand that a post-stroke patient has severe impacts on all the musculoskeletal elements, and they lose a range of motion and strength, which needs to be recovered. And in terms of upper limb, these are grip strength, joint torque, joint force, stiffness. These are things that we normally cover. And then this particular slide has few URLs mentioned for upper limb rehabilitation robots, which you can, in your free time, watch these videos and enjoy. Okay. So if you want, we can take a break now. Let me know if you want a break or you want to continue. Sorry,
Yeah,
let me
sure.
stop here first. Oops. So stop sharing and the recording. And so I was telling you that these are the addresses of websites of, in particular, I'm talking about 3 of the devices that are available commercially. So Hokuma company is I think far ahead in rehabilitation. They're selling Locomat for lower limb, and then they've got this Armio Spring for upper limb. Let me quickly go through a few of these commercial devices for upper limb rehabilitation, and then if time permits, I'll talk something about the robots and basic definitions. So we start from the simple ones first, and this is from MIT. So what happens is that these rehabilitation devices, you can classify them in broadly in 2 categories: one which are actuated, the other ones which are not actuated. Okay, so the ones which are not actuated, we call them, one second, I cannot see my, okay, yeah. And so the ones which are not actuated, they are called CPM devices, which means a continuous passive motion. Okay, so these are the devices that can provide continuous motion, which is passive, not actuated. So what I mean by passive and active is that if you're using a motor, for instance, or any actuator that moves something, then the device is called actuated device. And if it is only using spring, for instance, for the actuation. So what does spring do is when you stretch it and then leave it, it goes back. So when it's going back, it is moving, right? So this kind of spring motion, when it is used, the device is called as CPM, or a passive device. Okay. So this MIT Manus is very popular device. It was kind of it is existing for more than a decade, actually, for more than 15-20 years. They've been working on it, and fund is in the clinics now. So in total, it can provide you 5 degrees of freedom. So 2 of these are for the elbow and the forearm, for flexion extension and pronation supination, right? And apart from this, this device can also provide 3 degrees of freedom for the wrist, which means like you can do flexion extension, pronation supination, and also you can do adduction abduction. So these are the motion that this device provides. Now, remember I was telling you the difference between exoskeletons and end effector robots. So this is an example of end effector robot. So what end effector robot means is, okay, let me draw here and explain to you. Okay, so if you're talking about an end effector robot, so what it does is you've got a base where it is fixed, and then you have such kind of a rotary joint, let's say rotational joint 1, rotation joint 2, and then rotation joint 3, okay, for instance. And then here you have some sort of a grip to hold or something, okay. So the grip or the holder that we have at the end of the robot is called end effector, okay. W, okay, end effector. So in such kind of robots, the person is supposed to, hold his hand like this, okay, and then it would move your hand around. So if I'm holding it from here, if I'm holding my hand from here, and then if I'm taking it around, so that's how this end effector robot would move, right? Okay, so for instance, if I use such kind of robot, as you can see in this picture, the person is holding on the end effector of the robot, end part of the robot, and then this robot takes him around, and so this is the kind of end effector exoskeleton. End effector robot, not exoskeleton. The exoskeleton would mean that it has to be attached to the various joints of the body and goes parallel to the limbs. Yeah. Now, this is about the degrees of freedom of this robot and the capabilities, but they claim to kind of record patient's performance, and then accordingly they change robot forces. That's what they claim. And there are other devices. Well, if you talk about such kind of CPMs, there are at least 20 such kind of CPMs available. The important ones are this MIT Manus, and there's MIME, which is mirror image movement enabler. So there's an actual so you're given a trajectory, and then you move it, and then you can see it, and you know if you're doing correct or wrong. And this arm guide is again very popular, which is called assisted rehabilitation and measurement device. This is again an arm device, a CPM. There's another CPM kind of passive device, which is called T-Rex, this is again very famous. The T-Rex name comes from the fact that it is from Wilmington. So Therapy Wilmington robotic exoskeleton, that's the name of this robot, as you can see in the picture. And there was some video for this. If you want further information, you've got the names of these devices. If you want further information about these devices, you can check on internet. You'll find many interesting videos and you can see how these are working. But this is a passive device again, and it's different from the end effector device of MIT minus, because it's an exoskeleton. As you can see, the exoskeleton has been attached to the person's body. Okay, so this is a kind of a station where everything is connected, and there's a belt conveyor. These are the belts. Okay, so these are elastic belts. So when you move like this, it will take you back. So yeah, and yeah, let me clear this drawing. So they are now actuators, as I said. It can provide you the entirety of 3D space. Okay, the MIT minus was a planar device, where this is a 3D. This can provide you 3D workspace. You can rotate your hand in the 3D space, and they focus on the functional arc of the motion, which I was talking about before. You know how I was talking about the normal arc motion and the functional arc. So what they claim is that they can provide like 66% of the normal workspace, the arm in vertical, and 72% the horizontal. There's another such kind of a device called arm in, and it has more degrees of freedom. In fact, it has 7 degrees of freedom, which also provides you the shoulder motions. So 3 shoulder motions, 2 for elbow flexion extension and the pronation supination, and then for the wrist again, remaining ones for the wrist. So it comes with its own chair. Person is seated there, and the entire exoskeleton, its length can be adjusted with the person's limb size, forearm size, and as you can see, yeah. So in most of these devices, the person is supposed to be playing some sort of a game, and in the pretext of playing game, the wrist, elbow, and the shoulder joints are moved, and then they are recorded also. The motions are recorded also. This is a new device. It's called NXA2, and see, 1 second. Yeah. So this, as you can see, okay, this is the close-up of this. Okay. So this is the robot arm coming from the station, which you have here. Okay, and it is a movable station. Okay, so it can move. So the person seated would have this exoskeleton attached, and then it has various motors. Okay, and they work with a cable. Can you see this cable going down there? And so this is actuated like this. And then for the wrist again, you can have all kinds of motions. Right? So it has feature for arm loading and unloading. So you don't feel the weight of the robotic device. Okay, the exoskeleton, it provides you 0 gravity. So whatever is the weight of the exoskeleton, it compensates it, and you feel like there's nothing attached to your hand. You get feedback from the robot sensors, and yeah, you can perform targeted training, and there are tools to convert the sensor readings into some sort of an assessment and evaluation. So for persons suffering from hemiplegia and such as disabilities because of neurological disorders, well, there's cerebrovascular problems, and So all sorts of, as I said, can put into two categories like injuries and neurological disorders. For all these issues, for these problems, the disabilities caused by these problems can be treated with this robot. It's a bit expensive. It comes like more than 100,000 USD, which is a bit on the higher side. Now this Alex is very popular, and it's being used in many clinics. Yeah. So it's used for stroke and also for stroke and upper limb, especially, and also for the shoulder. Now, the important thing is you can kind of use one of these joints. For instance, either you can use it for shoulder or you can use for. So you can go for a selective rehabilitation, and yeah, it's basically an actuated one. So you call it active assistance. It's not a passive device. So as you can see, it provides you with the wrist motions here. Yeah, apart from that, it also has this kind of a jockey which you can hold on to. And so it has sensors into this jockey. So it also measures how much is your grip power. And then this part, it has two motors for, and so it gives 2 degrees of freedom at the wrist joint. One for the elbow and 3 degrees of freedom for the shoulder joint. This Amadio, again, is very interesting, but it's a kind of end effector based robot design. It only has this device, okay? And then it has these magnetic caps on the fingers, on the tip of the fingers. So, as I was saying, it's an end effector type of robot. And so it is designed for hand rehabilitation, of course, yes. And it has also this visual feedback from the screen and also interactive tasks. And in the process, you can measure many movements through sensors, and you can check the progress of the patient online. There's a video link for the video if you want to watch it. You can have a look. So, Hokuma, yes, please. Yes,
all of these new names that you're mentioning to us, Mu Power and some other robots that we just learned about them today, they were the questions, one of the questions in the quiz one, which I was really like trying to see where I can find the answers or where to read about them specifically.
Right. Okay. Yeah. So it's nothing scholastic actually to find these devices. The information is all over the internet, but so if you couldn't find some of these, don't worry. Because even if I want to collect the entirety of information on these robots, it's not possible for me. Looking at the variety of their characteristics, like some are passive, some are active, and those are passive. It comes with different degrees of freedom, which are those again. If you talk about the active ones, again, there's a whole lot of variety into those. There are end effector types, there are exoskeleton types, and then to show you, maybe I can show you sometimes. I probably have 3 review papers on this. So I myself have written 3 review papers where I was trying to put all these devices into paper, but still I could not discuss. And then by the time you finish your review and have a paper, there are more devices being offered, and people all over the world, they continue working on these things, and whoever comes up with a new design will try to publish or maybe advertise on some magazines, on internet otherwise. Some of these devices, they don't even, they are not even research products. These are straight away came from some companies. For instance, this RBO Spring and RBO Power. You would find very few journal papers or research papers around these. So
because a question was a bit, I couldn't actually understand the question. I read through the question so many times, like what does it exactly mean? Because it was talking about bioinspiration. Which one of them?
Right. Yeah, I remember that
because we
bioinspiration
didn't
question.
study about them yet. I really didn't know what's, is it the function? Is it the category? Like how?
Yeah, see, we did talk about this bioinspiration in the first lecture.
Yes.
If you remember that, right? So I was thinking maybe you would be interested to see what is bioinspiration and how it's been implemented in various other devices. So, for instance, if the robot arms have been designed to mimic, your forearm and the wrist and the shoulder joint, for instance, that's one kind of bioinspiration. The other kind of bioinspiration and how the robot is being actuated. Some would use cables, some would use those air muscles, some would use even motors, but then they try to make their motors look like being actuated like skeletal muscles. And then in the control system, some would try to use bioinspiration, bioinspiration in controllers would be that it takes input from your biosensors like EEG or EMG, and then it's being controlled. So that kind of inputs I actually wanted from you to read yourself. And so you're talking about
question 4. I wasn't
right?
sure if we are.
So what is bioinspiration?
Yes.
And then which are the functions of the following robots? Yeah, like Venice. We just saw this, right? T-Rex, Mine, Armio Spring, and Armio Power things. So you can, I mean, for that you need to actually read and understand what these robots are and what do they talk about bioinspiration, or do they don't, or they don't talk about bioinspiration at all.
Yes, because I think the question was a little bit confusing, saying which of the functions. So, and it was categorized A and B. So I didn't know if I have to choose A or B, or should I just talk about each of these robots and say each?
Sorry for not being expressive, because here I have got all upper limb robots, and here I have few of those lower limb robots. And I wanted you to find in these robots what kind of bioinspiration is used. So these are all rehabilitation robots. And I was asking you to reflect on the bioinspiration being used in these robots, whether or not bioinspiration is used.
Okay, so I totally misunderstood.
That's okay, no problem. As I said, this is not the first and last quiz, and the quiz is not just the only evaluation that we would do. And once again, don't worry, I'll be like more liberal, because I know this being the first quiz, and I may not have been very expressive, so it's fine.
And another question I have: the names of these robots are sometimes I don't know if it is a brand name or is it actually based on the action they have. Amio is more obviously to do with the arm.
Yes. Yeah, these are the brand names which people have come up with to also at the same time explain what they're used for. For instance, Armio Power. Okay, so Hukuma company has, again, I think 3 kinds of robotic devices for upper limb, and so that's why all 3 are called arm. So one which is actuated, one which is powered by motors, it's called Armio Power. The other one is not actuated by power, it's called Armio Spring, because they use spring. And there's another third kind of, which I'm forgetting. So the names they are brand names, but they're not company names. They are not company names. They are the brand names of a particular device. which also reflects their use or application. So this
Yeah.
Armio power, as it says, it's a powered orthosis. It's a powered exoskeleton, and well, so it has, for
Alex,
instance, if we talk about these, please.
yeah, Alex, for example, I think when I was looking it up, I think it just opened up a website of the company.
Okay.
So I wasn't sure if it's a brand name. Is it, yeah.
Yeah, it's a brand name, and it has a full form, something like active, and then exoskeleton. So active assistance. Yeah, I don't know what L stands for, but yeah, they normally create some sort of acronym or abbreviation like this. And yeah, for instance, it's very funny, but the gate exoskeleton that we have developed, okay, it's called, let me write something. It's called,
Thank you.
yeah, welcome. So I'm telling you the name of my device that I'm creating. So this is gait rehabilitation using exoskeleton assisted technology.
Interesting. Very
Yeah.
creative.
So they're all interesting names and very funny sometimes. Yeah. So this Armio power, as I was saying, they use this kind of bioinspiration in their control algorithm somewhere. Let me read through. So they use sensors, and they use this intelligent algorithm to find out how much is patient not able to carry out, and so to the extent that from the extent the person is not able to carry out further motions, the robot suggested. I mean, robot would assist it. So this is the kind of robot, as you can see. So it has 1, 2, and there's one more here. So it gives 3 rotation degrees of freedom of the shoulder, and then for the 1 for the elbow, and for the 2 for the wrist here. So yeah, and then it has this interactive screen where they can see. Yeah, so this is the back side rear view, and this is the front view. They can see it more clearly. Okay, so it does hand function training and arm weight, because it's quite hard, quite heavy robotic device. So it has to be compensated. So their motors, first what they'll do is they'll compensate their own weight. So that kind of actuation. And then they would, from that point, they would take the hand motion further on top. So let's say to keep the robot in a particular position, they need maybe 10 Newton of force. And then to move further, they need another 2 Newtons. So that's how they control their robot. It does some assessment, and it also has it's called augmented reality interaction to make the person play a game, and then so it comes in various designs. So this is for like elbow and this thing, wrist, and here, as you can see, used for shoulder, elbow, and the wrist. Yeah. So the previous slide where I had, those URLs from their websites, there you would see those 3 versions of Armio, Hokuma company, Armio Spring, Armio Power, and there's one more for that's again a passive device. It helps in kind of alignment. Yeah. This is again very interesting one. ExoGlobe, not ExoGlobe. ExoGlobe is again a different device, but this is ExoGlobe, and then a pro version of it. So it's just a globe. Okay, it's not an exoskeleton, but it can help in grasping something and for the hand motions, basically, wrist and the hand motions. It is built by Recessive Technologies and for stroke patients, of course, and they work with the motor functions for the wrist and the fingers. So as you can see, well, with the glove you cannot see what's inside, but inside you've got they've got a motor for each of the fingers and the thumb, and so they can be actuated simultaneously and they can be actuated independently as well to check the individuation of fingers and finger movements and for the corrections. This is Ryogo. So it is again a wheel device, and it's only for the wrist and the forearm and the wrist. So it's an exoskeleton, of course, because you can see it's been attached to the human limb, and it can move in 3D space. So this thing has got 3 degrees of freedom, so it can take you all around. Okay, and has got a fixed base, of course, and then there's an end effector arm, okay, and through which this is connected to, okay, and then when they say that they can provide some sort of shoulder movement, that is because of this arm. It can go up and down, okay, and so you can have some shoulder motion. Motor Plus is again recently been marketed very aggressively. This is the device, that's it. It's a very small kind of device like gloves, okay, and so it helps you in, once again, for the focusing wrist mostly. So what happens, you know, specifically in this stroke, post-stroke, mostly the movement has to be started from the wrist joint. So wrist is the main focus for therapy. And so we start from the wrist and then we go for the rest of the like lower limb part. So it's a battery powered device, and it can run for an hour after charging. And so it can check how much force and motion the person is able to apply, and then making an assessment, whatever is the deficit, they would provide a deficit. It's an improved version. The previous version also, I think the video which I have is for the previous version, but it's quite explanatory. I mean, watching this video would understand more about it. Oops, I'm done. Okay. Yeah. So if you allow me, I'd like to quickly go through the other one. Previously, we used to also, you know, go through. There's a software. It's called Robo Analyzer, and then you could see how a robot is constructed. But I'm skipping those details now because, as I understand, you guys don't have to know how a robot can be designed and made. Rather, you only need to know what are the definitions, because mostly it's the robot that you'll be using, not that you'll be designing one. So here in this file, I have some definitions for the robots and basic working of the robotics. With these slides, once we complete, we may not be able to complete all of this. I'll skip some of the details just to give you an overview of what a robot is, and there are few definitions and terminologies which are frequently used in rehabilitation robots papers, which if you try to read. And so to make you more conversant with this terminology, I'm using this, okay? So nothing like a rocket science, quite simple. So as you know, the robots is a programmable device which can work on its own. And so normally it has an arm, a wrist. So seriously talking about it, it actually has the entirety of its anatomy. Because robots were supposed to, were meant to be mimicking, human actions or working like a human. So the robots that we designed initially, their robot parts were defined to mimic a human body. And so we'll go through the robot design, which is essentially the robot anatomy. And then it has sensors, like we have eyes and ears. And it has a controller. A robot has to have a controller system, like we have brain in our body. The end effector would mean that the grip in my hand that I have, the wrist and the fist. And then we'll talk about a few more things, okay? So I'll rather go very quickly. So we use the robots and repetitive functions and activities which are hazardous, okay? So normally a robot would have joints and links, okay? So these are the joints, and between the joints, what you have is called the links. Now, there are two sections, body and arm, and the wrist assembly. So this is the end of the arm, and sometimes also called as the wrist assembly, and the remaining part is the body of the robot. Okay, let me go full screen. That makes it much easier. Yeah. So the robot joints can have various kinds of motions. You don't have to worry about, but this for your sake of information. The joints can move linearly like this. They can go orthogonal, like this is input motion. So it moves like this, and this is at right angles. So this is called orthogonal joint. Denoted by L, denoted by O. A rotational joint is denoted by R. A twisting like this is denoted by T, and a revolute joint would be something like V. So this goes like this. Sorry, not this. So when you rotate this, the entire thing goes like this in a circle. So it goes like this, okay? So that's a revolute joint. So there's a difference between rotational joint and a revolute joint. This is R and this is V. So for any kind of robot, for instance, we have such terminology. So you know that this, if a robot is defined as TRL, you would know that it can give you a twisting, and it can give you a rotation here, and it can give you a translation such as L. This is how we normally define a robot. So twisting, linear motion, and this is also linear, but this is orthogonal. So it'll be like TLO. Once again, this is L, this is O because orthogonal, and this is also O, so it'll be LOO. This is twisting here with a rotation and rotation, so it'll be like TRR. Okay. Likewise, you have many such combinations and definitions. So wrist assembly is the end of the arm, end of the robot. And we normally have some tools attached to this wrist, and it can have three motions called roll, pitch, and yaw. So a roll motion is this, you can see, okay. For pitch, it can go downward, or it can go upward like this. It can go like this. So roll is this is pitch, and this is yaw. Okay. So this about this axis, whatever is the movement, is called yaw movement. Okay. Yeah. So TRTR, TVRTR. So the robot body part and then the wrist assembly are defined like this. We can have actuators to move robots, and these actuators could be electric, hydraulic, pneumatic, or any other. These days we have very unconventional kinds of actuators, which we may not discuss because it's out of your context and scope. There are various control systems that are used, and for robots we use normally something called intelligent control system that takes into sensor inputs and the previous history, and then the controller has to make a decision on the further actions. So don't worry about the robot control. The end effectors are again two different kinds of. One is called gripper, and the other one is where you can attach many tools. So the tools one is used for the industrial purpose, and the gripper one is used for medicine purpose. Many grippers and tools are shown here. Now the robot can move, and the space which it can move is called its working envelope. It has coordinate system like we discussed for our human systems. So it has a world coordinate system, which is the global reference system we had, and then it has local reference systems. Okay, and then these can be mapped together. So from global reference system to the local reference system, we can create a mapping, and you can find out how they're related. It is shown how the workspace of a robot looks like. The circles that you see here, okay, that shows where the robot can actually reach and where the robot cannot reach. So outside this sphere, it cannot reach. So the workspace of this robot is a spherical workspace. This is regarding that coordinate frame transformation, which I was talking about, from global reference frame to the local reference frame. So what happens is, you don't have to go into the theory of it. I'll quickly go through. So for instance, if there are two coordinate frames, one is XYZ and the other one is UVW. Now UVW has been rotated by some angle, okay? So if it has been rotated by some angle, we can find out a matrix by which, if you multiply this, we get coordinates in UVW with respect to XYZ. Or what I'm going to say is that if there's a point P and I know its coordinate in UV and W coordinate system, if I know its coordinates, multiplying those coordinates with R, I can find out what will be the coordinates in X, Y, and Z. Okay, quite simple, isn't it? And how do we get that matrix which I was talking about, multiplying which you can transform these? So here's an example. If the coordinate system has been rotated about x-axis, use this matrix. In this matrix, the C stands for cosine, and S stands for sine. Those who understand trigonometry, they can figure out this is cos theta, this is minus sine theta, and so on and so forth. And so sometimes the coordinate systems, they are translated and then they are rotated. Okay, so if there's a local reference system and you want to map with the global reference system, so I'll bring it here. So that's a translation, and then I will align with it. So that's a rotation. So there are two things required: translation and rotation, and then the local reference system can be exactly overlapped on the global reference system. So the matrix that I was talking about, that magic matrix, it has two parts: a rotational part and a translation part. So put together these two, it makes one matrix, which is called a transformation matrix. So it has both parts. It has rotational part and it also has translation part. So the sequence of rotation and translation, it does matter. So what happens is, like, if I take my, okay, if I, for instance, if I add 2, 3, and 5, I get 10, isn't it? And if I add 2, 5, and 3, the result is still same. Or if I add 3, 2, and 5, the result is still same, isn't it? Yeah, but that doesn't hold true with the rotation, with the displacement, angular displacement, rotation. So if I take my mobile, okay, and if I rotate it about x-axis and then y-axis and then z-axis, I get a certain portion. But if I change the sequence, the resultant portion would be different. Okay, so that's something important. And so yeah. So this is what I was saying, that this is your local reference system, this is your global reference system. So for local reference system, global reference system, if I need to find a mapping, that means I'm trying to find a magic matrix by applying which it'll give me the coordinates in the global. So what I need to do is I need to convert it back to, I mean, try to make it overlap the global. And so this is called a transformation matrix, which will relate location of point in third reference frame with the first reference frame. So if you rotate about, let's say, x-axis, y-axis, and z-axis, so these were those matrices and they can be put into one. Don't worry about anything. Here's an example, a quick one to show you what I'm trying to say. Strange, wait. Let me change this. And you've seen so many slides already, isn't it?
Yes.
Yeah, so this is the last one to show you what this mapping was. So here, what I have is a point P, let's say, okay? And then if it is rotated by z-axis, y-axis, and then it is also translated by some amount, okay? So what happens is, this 732, okay? 732 means this is 7, this is 3, and this is 2, okay? After all these transformations, it becomes 6, 4, and 10. So it becomes 6, 4, and 10, right? But if you change the order by which they've been transformed, like you rotate about z first, and then you translate, and then you rotate about y, then it becomes a different thing. It goes something here. So the only objective here to show you that the order by which we rotate these matrices it changes the end position. Here I was talking about the degrees of freedom. So I already told you that a point in space can have 6 degrees of freedom, and the degrees of freedom are translational and rotational. Sometimes they can be together. There's a formula to find out what are the degrees of freedom for robots. We normally go with this kind of formula. For instance, okay, there's nothing that you need to actually remember or understand, but only if you can follow. If this is a formula by which I determine like how many degrees of freedom a robot would have. So this L would mean number of links. J1 would mean number of joints with 1 degree of freedom. and J2 will mean number of joints with more than 1 degree of freedom. So this is some sort of a robot, let us say, okay, and so it is connected with the ground, and so ground also become a link. And then there's one link here, and this is the third link, okay? And these are the points where it has been pivoted. So these joints can move like this, okay? So this is 1 degree of freedom, this is 1 degree of freedom. So all these joints, they have 1 degree of freedom. And since there are 4 links, 1, 2, 3, and 4. So this is 4, sorry, this is 4. And how many joints with 1 degree of freedom? So I've got 1, 2, 3, and 4. So I'll place 4 here as well. So it turns out that this kind of mechanism would give me 1 degree of freedom. That's it. Nothing more than this. And then there are some difficult calculations on degree of freedom. You don't have to worry about it. This is only for your information, okay? This file is not supposed to be in your scope of course. This we normally use for like teaching our students in robotics, so I'm just using it. There's another thing which is interesting. Sometimes people use it in rehabilitation robots. You know, when you read the papers, you would come to know about these terminologies. So, for instance, you have such kind of a robot. So this robot has link number 1, 2, and 3. Okay, and joint number 1, joint number 2, and this is your end effector, which can also say this is joint number 3, right? So this makes the entire robot. Now sometimes I know what is this L1, L2, okay, and what are the angles. If I know these angles and the lengths, okay, I can determine with the coordinate system. I can find out where this point is. I can find out the coordinates of this point. Okay, so this is called forward kinematics. And at times, I'm given the coordinates of this point, and I need to figure out how much is the length of this, how much is the length, and what are the angles. So this is called inverse kinematics. Okay, so when you move forward, it's called forward kinematics. When you move backwards, it's called inverse kinematics. Yeah, so once for the next few slides, I'm talking about this forward kinematics and the inverse kinematics, which should be, I mean, you should just need to know that these are the terminologies, and sometimes you may come across these things. Talking about this workspace of a robot. So for instance, if you have a robot which can have translation when it has 2 links, and these 2 links can move like this. So this will be the workspace, and we call it a planar workspace because it's a 2-dimensional plane. So a 2-dimensional workspace can be like a circle or a disc, or it could be annular kind of thing, because so this link can go around and can go like this. So this is the area where this end effector of the robot cannot reach, because it can go like this. Oops. Right? So this is the unshaded area is the one where it cannot reach, and so the shaded area is its workspace, and otherwise, which is not shaded, it's not its workspace. Yeah, there are calculations that can be done. For instance, this robot, it has reachable workspace. So it can only reach to the shaded area. Similarly, this workspace can be a three-dimensional workspace. Yeah, I think I should stop in here. You already know how much you should know about the robots. So what we didn't talk about is what are different kinds of motors, and I mean basically you don't need that information. It's working information that you needed, and I think you have it now. For your interest, I'll share these slides with you as well if you want to just go through. It's only to help you understanding the various literature that comes with the robotic rehabilitation robots, so that you should be able to understand. Apart from this, I had shared one file on vectors, which gives you a fundamental information on what are vectors, how we can add vectors, how we can subtract vectors, how we can multiply vectors. This information is normally required for carrying out some certain experiments in the biomechanics lab. Though there are software which can help you determining these things, but you should know the basics of vectors, matrices, and determinants. Yeah. So, yeah, this is all I have for today, because I don't want to start with a new topic, so it should be fine. Yeah. If you have questions, we can discuss. Also, I need to know if what we discuss here does it, it interests you or not, or anything other than this. If you need, for instance, you might tell me like, Professor, we need more information on a particular area. For instance, if you want to know more about a particular kind of robotic system for robots for rehabilitation, you can do that. But like we discussed today, basic anatomy and biomechanics for the upper limb, and then related devices that are being used for upper limb. We discussed the biomechanics, and then how this biomechanics is compromised with the stroke, for instance, and then what are the devices being used for. But it was a general kind of review. But then later we'll talk about there are specific elements, and there are specific robots designed to match for, specific rehabilitation robots to cure a particular specific problem. So we'll do that kind of study as well. So this is what we have done for the upper limb. We'll try to, maybe the next lecture, we'll do the same for lower limb. Okay. So if you have suggestions, and if it's possible for me to incorporate, I can do that. And you have the entire course planner with you, I think, in the form of that brochure. So that gives you an idea of what we are going to cover next, apart from those lab sessions. Yes, please. Any suggestions or comments or questions? We still have some time.
Just thank you. Thanks for your lectures.
Yes, so
very interesting.
Is everyone here now in Astana? Adil is already here, right?
Yes.
Yeah, good. So if I kind of schedule something for this demonstration on Thursday, how do we make a meeting time, or schedule a meeting time? Because for coming to the lab and for the sake of demonstration, you don't need any PCR or something. If you're inside the campus, you can anytime come and visit. But those who are out, is there someone outside campus? I'm pretty sure.
Outside campus.
Adil, you are outside?
Yes.
And do you have access? You don't have access?
I don't have access.
And to get access, you need RT-PCR test done. Mashi, can I ask, are you on campus or not?
I am on campus, but the labs in the Nozum building, or is it here in the actual NU?
Yeah, main campus, C4.
Main campus.
Yeah.
Okay, that's easy.
Mhm.
Yes, I'm
Yeah.
here in the campus.
So yeah, Adil can come online. If you can arrange for your access, it's well and good. And if you cannot, you can be present online.
Okay.
Yeah, we can organize a Zoom meeting with him and show him around with a mobile phone maybe. So I'm planning tentatively for Thursday. Time, to me, I'll be more comfortable for, where's my calendar? Let's go. So Thursday, sorry?
From 10, we have lecture from 10 a.m. to 1 p.m. in Thursday.
Yeah, sure. I can quickly take you to my calendar on Thursday. So, okay, these are some interviews that we're conducting. Then we've got the Students Emergency Fund meeting. We have time here. Oh, she's busy. Okay, after 1:30, and then when it's town hall. So any time after 3 to 6, I'm fine on Thursday. Yeah, Thursday 3 to 5, anytime that you mention, if you're comfortable. So we'll discuss this further on the WhatsApp chat. Okay. Good. Thank you all once again. And yeah, I hope you enjoyed this session, and do write me your suggestions, comments whenever you get time. Okay. That's very important for us. Okay. Yeah. All the best.
Thank you.
Bye-bye. Bye.
Bye.
Okay.
Thank you.
Bye.